through this particular data set. So my name is Shan Sudharan. I'm at UNC Greensboro. And on the left side, you can see visit my website QR code. So you can take action my website. But I also have in the last slide, I have all the details as well. So the very first thing always we need to think about in my talk at least. So I mean it's a generic idea that we always think about the problem domain. So if we don't really understand what the problem that we are addressing, then it's going to be an issue. So here, the simple thing in machine learning perspective, the classification of objects. So obviously the objects are coming from the data domain. So the machine learning is being used either for prediction or for a classification of objects, and for example, leaves or healthy leaves and unhealthy leaves. They are objects, considered objects. But the contribution of this talk is not just a classification, but classification of objects under constraints. So what we are looking at, the actual compressed domain. So if you have a compressed domain, so not the original data, but it's compressed already like a dimensional reduction, then how do we learn from that particular data under constraints? But most of the data are actually constraint-based. So the equation that you see, this is the regular machine learning that we are talking about. Say, for example, if you input a plant leaf, either is a healthy or unhealthy, then we really need a learning model or machine learning model F that can actually predict whether it's a healthy leaf or unhealthy leaf. So this is a parametric model. So we learn these parameters alpha and beta. So that's the simplest equation that we could do it for machine learning model. But the constraint models, what we are talking about, this is basically the compressed, dimensional reduced. So when you do that, so then this prediction is also constraint based, and that may not be the same as this one. So there's going to be an error there. So how do we address that kind of problem? So I just present a very simple example. So here you can see the unhealthy leaf, apple leaf here, and that's the original. It's not yet original, but without these the compressed details. But here you can see that if this is compressed, then can we detect the object or classify the object? So the one way to do, probably you basically have to find a technique to reconstruct the original. But when you reconstruct the original, you can see then still some of the information lost. But here there's many information lost. So same problem. So not just plant leaves. So anything that we can do is actually the compressed domain that we are talking about. So most of the data, then when we look at it, if we don't produce, then we're probably thinking that these are original data, but it could be compressed. We don't know. So what we really need to have that basically under the assumption of compression, compressed domain. So how can we build the model? The other thing actually what we could do is that we probably want to share the image or the data set, so then we can probably to save the storage and then the transmission efficiency, we probably compress and then send it. So when you receive a compressed data, then how can we build the model? So that's what we are looking at here. So however, the beauty is that the compressed domain has unique data characteristics. So they may have sparsity. So the sparsity could be a problem as well as a solution. And then the reduced feature correlation. So some data, if it's original, there may be a lot of correlated features. And then the Gaussian approximation is possible with the compressed domain. And the random orthogonality, that means that because of compressed domain, you may have different versions of compressed domain. So from the same data set. So each set of data could be orthogonal to each other. So that's another thing. So then the other one is the preservation of the pairwise distances between the feature vectors. And also the inner product preservation that could help the Hilbert space analysis. So as we can see here, these two are the original leaves, healthy leaves, and these are unhealthy leaves. So So why we do all these things is to understand the problem and also to understand the sparsity in this particular problem space to develop the meaningful solution. But the key thing is that we really need to extract features. As you can see, when we see these things, so we can see the features, for example, and then give you the impression of the original leaves. But here you can see the unhealthy leaves. So there are some features hidden. So we really need to extract those features. So here, this is the data set I've been using in this research, and especially this the disease of the leaves is a cedar apple rust. It's basically a fungal rust disease that we see. So the feature space. So because we talking about the features, so we need to construct the feature space. But when you construct the feature space, we have currently in the data science, we construct feature spaces, the collection of feature vectors. But the thing is that actually, can it be used as a feature space? Of course, a feature space, but it has to be futuristic. So in other words, can we encode that into future learnable representation? Can we keep representing to learn when the new data set is coming? So the beauty of this, the thing I'm going to talk about, it actually preserves the inner product of observation, inner product between the feature vectors. So therefore, it's applicable in a Hilbert space. We can apply distances and then angles and the directionalities and things like that. So just to simplify, as you can see that we can see the two-dimensional features here, but we really need to construct the feature space. So how do you construct the feature space? The best way to do that, actually, you can flatten each one of them. So if you flatten them, this is 128 by 128 image. If you flatten them, it's going to be 16,384 features, right? So you can see that you can put this column, but I'm just giving us just a toy example to show you that there are, say, for example, 6 features. So this is the 1D array that comes from the flatten the data, but it technically should be x1 through to x 16,384. And this is the second leaf, and then third leaf, and fourth leaf, and keep going. But when you look at it, this one is a vector that actually the healthy leaf, and this is the healthy leaf. And when you do the third one, unhealthy leaf, and this unhealthy leaf. So we have to construct something like that. But the thing is, actually, this data set is basically condensed. So so this is not compressed. So there's no sparsity. It's like that. But that means that all the information basically hidden here. So that making the machine to learn the actual characterization is much harder. So therefore, that's the reason we're looking into dimensional reduction. But the dimensional reduction, there are many techniques. Not always every technique is useful in terms of achieving machine learning. So one of the dimensional reduction, very popular one, is the principal component analysis, PCA, but that uses the eigenvectors of the covariance matrix of the data. Then the independent component analysis, that basically uses the statistical properties of independence of variables. And then the sparse random projection basically uses the distance-based. So it doesn't care about the correlation or independent between the features, but mainly is actually trying to find the dimensional reduction with respect to the actual distance between the vectors, the feature vectors. So which one is good in our application? Because of the sparsity. So when you have sparse, so distances are important, because if you look at there are many points there, then if it is sparse, then you can measure the distances. So rather than looking into the eigenvectors of the covariance as a global characteristics of the data. So therefore, in my talk, I'm using the sparse random projection for this purpose. So let's look at the modeling. So this is called compressed sensing and compressed learning. So this is the two distinct definition that we always use to understand the machine, how it learns. So if you look at, this is I've already shown this one. This is the regular machine learning. So this is the compressed domain machine learning. So if you look at the difference between these two, So that's where the compressed learning comes, because you want to learn this from this. So we need to minimize this distance, so like that. And then for a compressed sensing, that you basically transform that because you want to sense. So you need to have a function of x rather than just exactly minimizing the distance. So in other words, in other words, it's basically extracting some features, features from that, and then sensing it. So the idea is basically, how do you find this function? So more visuals, as you can see. So this is the original feature space as an example. So if you transform through the sparse random project in SRP, then you can feel like, okay, so this is that a lot of compression takes place. So you can learn here from that and then see whether it can be predicted, how far they are. The other way to do it, basically, you build a model from here. So that's a G model that I showed you. So G model. So you basically, that's a sensing model. So you do that and then you reconstruct. So what will happen in the future, if you have a new data set arrives, then you can say, if you have already built something, the compressed sensing model, you can basically reconstruct the original, and then you can train the model here rather than here, because this is going to be big difference there when you do the compression, right? So that's basically the idea. So the compressed sensing is building a model between the compressed domain and an original domain to reconstruct the original feature space from the compressed feature space. So that's a very simple, simple definition that we could give. So the sparse random projection is a statistical tool that help us to generate, the compressed feature space for modeling and simulation that we can do. So visually, we could see that how we can do the dimensional reduction is, we know that this is a matrix, say, for example, 6x9. But I already explained to you how to generate this with from x1, x2 up to x16,384 from a 128 by 100 image size. And then you may have a many number of images here. But now it's a toy example. So 6 times 9, if you have 4 times 6, when you multiply, you have a new set 4 times 9. So it's already basically dimensional reduction taking place. But what will happen actually, if we use the eigenvectors of the covariance matrix here, this becomes the PCA, the principal components, all of them, right? And if you do the independent analysis, so then it's going to be independent component, and then meaning that each one of them are independent statistically. But the sparse, because you want to do the distance, so you basically create a random sparsity here. So you can see the white there are zeros there. So it means that when you have a larger dimension here, then you may have many different randomness that you can create in this matrix. So therefore, a lot of randomness going to come here. So every feature that arises from here going to have some sort of statistical PDF probability density function. So then we could use like a kernel density estimate or something like that. So for a G function, that sensing function, so we could use kernel-rich regression. That's what I'm using here. There are many machine learning models you could use, but I am using the kernel-rich regression here in my simulations. And then also you can do the deep learning, to do the compressed sensing part. So that's the G function that you remember that we need to build. If we build it, then we can always sense from a given data about the originality of the original data. But compressed learning is very simple, it's straightforward. So under inside the compressed domain, basically you build a model to see that actually whether it's closer to the original or not. So for that purpose, I have used random forest. So you can see the KRR, kernel-rich regression, and then deep learning, and then the random forest are used. So just to get a very clear picture, as you can see, if you do x minus xc, that's the difference between the original and the compressed domain, then that's a compressed learning. But if you use the G function that for the sensing, So then that becomes the compressed sensing part. So this is the essential part that we need to reconstruct it. And then the added one here, it basically, because this XC coming from that random matrix, as you can, the sparse matrix, so it's going to be a lot of randomness. So therefore, that we could use some kind of learning here, which is for the explainability. So that creates the explainability function. That's basically added. So in that process, that's what you're going to take. So your original, and then you have a compressed domain. So each feature coming from some probability density function. So then what we could do, we basically apply kernel density estimation. And after that, you basically apply G. After that, you sense it rather than sensing it inside the compressed feature space, and then find the distance between that. So in that case, basically, we can allow the explainability on the results. So in other words, we are looking at are the reconstructed images meaningful? So because we can tune. Because once you have a kernel density estimation, then we have the bandwidth for the Gaussian distribution. As an example, if we use that as a kernel, so we could explain by looking at the features versus the responses. So that's what basically it happens. So Kushani, stop me anytime. So just
sure, we have time.
In terms of the time. Okay. So now so that's the concept that I just talked about. So now I'm going to talk about the simulation. So I'm going to show you the results that I obtained through the simulation. So the same data set is used. So as you can see, the number of images we use for the training and testing that going to come up in the simulation. So that's the data set I have used. So I have this in corner what exactly we are doing in the simulation with kernel ridge regression. So I'm going to use the kernel ridge regression to sense it here. And then when you do the kernel ridge regression, so we really need some kernel. So in this particular case, so there's always justification. We don't want to apply something that is being given in the function, so you apply. But there's a reason for it. So here, for the kernel, I'm using the radial basis function. But what is the reason? Because the data is scattered. Because especially when you have, disease on the leaf, I mean, those features are scattered. And also when you have a sparsity, when we apply the compression, that also creates scattered. So we have the data is scattered, but also we are looking at the distances. So eventually what we really need a smooth surface, like a function. So that represents these characteristics. So therefore, RBF is basically really a good function to apply. So that's why we selected the kernel here, for that. So that actually without KDE. So I'm not using the KDE at all. So I haven't talked about it. So the training, when we're done, as you can see that I use for the training 3,392 images. Each image is 128 by 28 and then 3 bands, RGB. But I'm only showing the grayscale images here. And then so that's that way that you have the white train that label. So it could be healthy or unhealthy, but 3,392. And then once you build the model, we're going to test it. So it's basically a 10%. So training on 90% and then testing on the 10%. Because the compressed domain, I just want, instead of doing 80-20, the first phase I'm using 90 and 10. So the accuracy of the original data by using all these without the compression, the machine learning models, random forest is the one used for the compressed learning, that give you 0.99 to 94% accuracy, which is, of course, is good. So now, after compression, then the particular compression I did, and it's going to be 0.91. So you keep it. But when you reconstruct using this G, which is the KRR, and then the reconstruction error between the original and the reconstruction, the 682 is basically lot. But lot does not mean it's bad. So you don't really want to have a closest one because we are not looking at the numerical distances. We are looking at the characteristics between them. So what is really extracted? So like that, okay? So it's basically a little way, but there's some characteristics that might be useful. But the problem is actually that characteristics and then the test data error is actually significantly high. So therefore, there's a distribution drift between the training and the test data. So if you train on that, and then testing on that is going to give you a very bad accuracy. As you can see here, the 0.46 error, right? So 0.46. So that's okay. I mean, that's what it's about. So now what will happen if I use the KDE? So in the KDE, I'm applying the KDE in the compressed domain in order to, without creating multiple domains, we are using the KDE to estimate the global parameter, the population parameter. So still the original data never going to change, 0.94. But the compressed data here, because of the KDE, it certainly bring it down to 0.74. But when you reconstruct through the G function here, right, you can see that from 2,747, it basically 811, but they're closer to each other. This also reduced. So that means that the reconstruction is getting better with that. Because of that, when you train on that and testing on that was 0.89. So KRR alone cannot do anything. So, but with KDE, it can do it. So that way, actually, we are bringing in the statistics domain into machine learning here, convinced that basically, okay, the KDE is doing. So there's explainability there. We'll talk about in a few minutes. So I've conducted a different simulation to show. I don't know whether I need to go each one of them, but you can see the compression accuracy is 48%. And here the simulation compression is 0.7%, 71 accuracy. But the thing is that this is with the KDE, with the bandwidth of 1.0. This is the bandwidth of 3.5. And this is bandwidth of 5.5, and then this is bandwidth of 7.5. So those are the differences. But you can see the compressed accuracy also increasing, 48, 71, 74, and 77. But the reconstructed one, as you can see, 77%, and then 88%, and 89%, and then 90%. So it basically reached, you can compare the MSE also getting closer and closer. So this is basically with the KRR, with and without the KDE. So that means compressed sensing is working. Without KDE, it's not that good, but with KDE, is doing good. So the results that you can see that, but the results, as you can see, that I ran the simulation 3. So the machine learning making the decision for the prediction as a healthy, it basically this way. So it basically cluster into 2 and then do some comparison to make the decision. So if you have one leaf, you're dividing the leaf, and then, okay, so we can compare these and say, okay, so they look the same, so they're going to be kind of healthy. But here, this way, looking at it. So this is the way you could probably explain, but I haven't done the fully explainability here, but I'm giving a platform for the explainability, because that way the statistician can get into and get into interpreting, not interpreting, explaining the actual results. So now KRR, I'm going to replace with deep learning. So it's very interesting. So when you do the deep learning, so everything the same data, 94%, and compressed learning is 94, but it's keep learning, as you can see here. And then eventually it reached the reconstructed error almost equal and also much lower. And then the accuracy, hence, is 0.992, even without KDE, right? Without KDE. So you don't really need a KDE if you use the deep learning. So that's what the beauty of deep learning is about. But then the question is, why do we really need KDE? KDE is for the explainability purposes, right? So because the KDE giving us different bandwidths. So by changing this bandwidth, so you can see the effect on the regions, and then you can start explaining it, okay? So that's why we are using the using that. So this is the the results, as you can see, that these are the regions being used for the purpose of predicting and giving the final results, prediction result. So compressed sensing with KDE for explainability. So compressed sensing model achieves high performance, but KDE can add explainability to the approach, as I mentioned to you. So here, the similar thing. This is the 48%, as we know, and then 71%. But as you can see, the DLL, it basically improving it. That you could look, so take a look at it, right? So yeah. So now this is from the KDE plus the deep learning part. So that's what this results is about. So the different regions have been used for the comparison purposes to make the decision. Okay, so the conclusion is artificial intelligence systems should incorporate compressed sensing and compressed learning because you can continuously learn. And then by integrating sparse random projection, kernel ridge regression, deep learning, and random forest technique, artificial intelligence system can perform better based on the results I have shown you. Then the artificial intelligence framework can also benefit from the kernel density estimation. So that will lead to explainable AI. So because in the artificial intelligence systems, the direction that we are going is to make all the AI models to be more explained. So these are some of the references that I have used for this class. And then any questions, and then thank you.
Thank you, Professor Shan. So are there any questions?